All right, so we might get started now. I'll just make sure everything's working. So welcome to the Special Vision series. So I'm Saskia, by the way, like the leads presenter, and then I'll introduce you guys to a couple other people in a sec. So firstly, we just want to start with an acknowledgement of country. So we just want to acknowledge the traditional custodians of the land we gathered on today, and I pay my respects to the elders past and present, for they hold the memories, traditions and culture and hope of Aboriginal and Torres Strait Islander people across the nation. My name's Saskia. I'm the Maths 3-4 tutor at Skyline. So I graduated in 2020 and I'm currently studying engineering at Monash. And yeah, other than that, I just love playing sport. I do a bit of netball and stuff, and traveling. And that's just a photo of me and my dad last year on a road trip. Cool. Okay. And then next slide. So just a bit of Zoom etiquette, just at the start. So this is a webinar. So I'm sure you guys have been on them a few times before, but we'll be monitoring the chat, like the Zoom chat. So you can ask like some quick questions and stuff in there. If you want us to go over anything again or anything like that. So for immediate questions, but if you have any like general questions, so Q&A type questions, we're going to be using Mentimeter. So if you guys log into Mentimeter, I think it's like menti.com. We might have the website or something in the chat. But if you guys log into there, we've got the password on the other slides, I think. And you should be able to ask like Q&A questions at any time. So just an agenda for the session. So it's like a 3-hour session. So we started at 10. So we'll just go through a quick introduction and then we'll cover like area study 1, 2, 3, 4, 5, and 6. So we've got a couple little breaks in there. For 10 minutes, so one at like 10:55 and one at 12:10. But yeah, and just throughout the session, we'll be going over just a lot of exam questions and content and stuff like that. Yeah, so we should cover everything like generally and go over a range of questions with different difficulties. Okay. Yeah, so this is like the Mentimeter slide. So if you guys could go to menti.com and just use that code that's highlighted there to log in. That's where we're going to be doing Q&A for the session. So yeah, I think Nan just put it in the chat to everyone. So if everyone could go to that website and just log in, that would be great. So you guys can ask us questions then. All right. Also, I'll just share my screen just so we can check that everything's working. We just wanted to do a quick survey of you guys to see how you're feeling for the exam right now. So I'll just try to share the Mentimeter. All right. Okay. Yeah, okay. So hopefully this should be working. If you guys can log on to Mentimeter and just respond to this question, just how confident you're feeling for the exam. So you should just be able to rate it out of like 5 or something. Perfect. So we're getting a couple of responses. Yeah, so we don't expect you guys to be super confident yet or anything. You've still got like a lot of exam study to do. So cool, 2.4. That's like, all right. Great. So yeah, we just really wanted to check how you guys are feeling at the moment and whether like your Menti was working. Okay, great. Yeah, so it looks like we're sort of settled around 2.5. All right, I'll just go back. All right. Yeah, so during the presentation, please ask any like Q&A questions to Mentimeter and that will be all good. Okay, so session expectations. So obviously it's a 3-hour session and Special is like quite a big content heavy subject. So we won't be able to cover like all variations of every question, but we'll cover like sort of crucial and commonly tested elements of the study design. Yeah, so the main sort of goal is to be able to like review all key sort of content components and demonstrate how like examiners will test our understanding of them. So we'll be focused mainly on like exam questions and going through content. Cool. Yeah. So that's our main aims. We got next. Yep. So then we'll just jump into Area Study 1. But yeah, so before we start, I just wanted to just introduce the rest of sort of the panel. So we've got Nan is our supporting tutor. So she's the special tutor for Skyline Hatch. So she takes the weekly classes. So Nan, if you want to say hi, feel free.
Hello, everyone.
And then we also have Arn is going to take the probability section at the end. So he's also one of the maths tutors at Skyline. So do you want to say anything now?
Yeah. You probably see me around for like the methods and all, but if you haven't seen me, hello, welcome.
Perfect. And then I think we should have Justine now. So Justine's from UBS, who's partnered with Skyline. So we just wanted to say a big thank you to them. So we would like to thank UBS for their incredible support. So they've been supporting us for the last couple of years with the exam series. And it's thanks to UBS we were able to run the revision series for VCE students. We also have amazing volunteers from UBS. So we've got Justine here today to help us with any questions and stuff. So we just want to say thank you to UBS.
Yeah,
cool.
I'm happy to be here.
Thanks, Justine. All right, great. So now we'll just get into the content. So we're starting with Area Study 1. So we've got rational functions and trig functions that we'll be going over. So Area Study 1, functions and graphs. All right, so the first bit of content that we're going to cover is rational functions. So rational functions is like what we're going to begin with for the session. So they're just like regular functions, but in this form here. So we've got p of x equals f of x divided by g of x. So where f of x and g of x are just functions. So in general, we've got it's defined just as long as g of x doesn't equal 0, because we know we can't divide by 0 because then it is undefined. Cool. So in special, we're expected to sort of understand how to graph them, which can be a little bit difficult because they appear like very sort of weird when we see them, but there's quite like a formulaic approach that we can take to graph them. All right, so this is like the general method that we want to use for them. So firstly, we want to factorize the denominator of p of x. So we do that to work out when it's equal to 0, so that we can do the second point, which is identifying vertical asymptotes by solving for when the denominator is equal to 0. Okay, so then the third point is just identifying the horizontal asymptotes by understanding the graph at extreme values. So that's working out like the y asymptote, so y equals whatever. All right, and then the fourth point is identifying any intercepts, so the x and y intercepts. All right, so we've just got this question here that we're going to go over. Yeah, so this is just like a general exam question that asks us to graph a rational function. Okay, so I'm going to change and share my OneNote, and we are going to go over them on the OneNote. But yeah, just letting you know, you'll have access to all the OneNote and the workings and everything. So it will be all like at your disposal. Okay, so hopefully you should be able to see my OneNote right now. And we'll go over this question. Okay, so for this one, we've got, we want to sketch the graph of f of x equals x plus 1 over x squared minus 4 on the axes provided. Okay, so the first step, as I said, was to factorize the denominator. So the denominator, we've got x squared minus 4, so we should know that that's just a difference of 2 squares. So we can say f of x is equal to x plus 1 on x plus 2 times x minus 2. All right, so now we factorize the denominator, we can do the second step, which is just to solve for when the denominator is equal to 0. So we can say x plus 2 times x minus 2 is equal to 0. So therefore, x equals plus or minus 2 are going to be our asymptotes. So we put them in there. So this is x equals minus 2 and x equals 2 is here. Equals 2. Cool. All right. And then the next step was to find the horizontal asymptotes. So the horizontal asymptotes like a little bit harder to find, So this is just like the sort of y asymptote. So in general, we can sort of think about it a couple of ways. So generally, if we have a function that we sort of expand out, if we're left with a function that's like f of x equals sort of some function plus c, which is a constant, that c value is usually the y asymptote. So we can see in this case, it's sort of like plus 0. So the asymptote should be at y equals 0. We can also check this by sort of subbing in y equals 0 into the equation and seeing if it equates to an undefined sort of value. So in this case, if we sub in y equals 0, we get 0 equals x plus 1, not x plus 2, x plus 1 divided by x plus 2 times x minus 2. All right, and then if we sort of solve by swapping the denominators, we can say x plus 2 times x minus 2 is equal to x plus 1 divided by 0. Okay, so you guys can see we've divided by 0 here, so this term here is actually undefined. Okay, and because that's undefined, that tells us also that y equals 0 is our asymptote. So we've got here y equals 0. And we need to always make sure that we're drawing the asymptotes and making them like a little bit obvious for the examiners. Okay, so that's our last asymptote. So now we can solve for the intercepts. So we've got the y-intercept first. So we just make x equals 0. So then we get f of x 0 plus 1, so 1 on, and we can sub it into either form. I would say like the original form is a bit easier. So it would be 1 on 0 minus 4. So it's going to be negative a quarter. Okay, so that intercept is going to be like 0, negative a quarter. So we'll put that in, and it should be round about here. So that's negative 1. So this is going to be negative a quarter there. So 0, negative 1/4. Okay, and then we also want to look at the x-intercept. So for the x-intercept, we make y equals 0. So we've got 0 equals x plus 1, x squared minus 4. So either form is fine. So if we solve this for 0, we just get the numerator is equal to 0. So then just x plus 1 is equal to 0. Therefore, x equals 2, negative 1. So we'll pop that in as well. So that's going to be negative 1, 0. Okay, so now we can see sort of the shape of the middle part. So the shape of the middle part, it's going to sort of approach each asymptote on either side. So it's going to come down like this, go across, and then down like that. Cool. So we just need to make sure the shape is right so that it sort of like approaches the asymptotes and gets closer as it approaches them. All right, and then in these two sections here, it's going to do the same thing. So it's going to sort of go from one asymptote to the other, but it could just have sort of two shapes. So it could kind of go like that or like that. So we need to work out. And the best way to do that is just to find like a couple of points just to see what it's going to look like. So I'll just find like f of 3 to work out what it's going to be like there. So if it's going to be above or below the asymptote. So f of 3, I'm sure you guys can do this. We just sub in a value. So we'll just skip the working out, but that's going to be equal to 4 and 5. So it's going to be positive. It's all that we cared about. So we know the shape is going to be like this. And then we can do the same thing with negative 3. So f of negative 3 is going to be negative 2/5 when we work it out. And that's a negative value. So this is going to be the shape of that one. Cool. Okay. So that's that question. So it's 4 marks. So they would be looking for firstly, like all of the asymptotes in the correct location. And we want to make sure we label them. So there they are. Then they'd be looking for the intercepts. And lastly, they'd be looking for the shape. So if we cover all of those things, we should be all good. All right. So we'll go on to the next question. I'll just share the slides again. All right. So next we're going to be looking at trig formulae. So for trig formulae, there's a lot of formulas like on the formula sheet. So I've got that sort of a picture of that written down here. So we're going to be expected to use sort of all of them and be able to apply them in different situations. So you're not really expected to memorize them because they give them to you on the formula sheet, but it's good to have like a general understanding, and it's good to like memorize sort of a couple of them that are used more often. But honestly, these were sort of the one group of formulas that I didn't really memorize just because there were so many of them, and they are on the formula sheet. So we'll use them in the next example that we've got. All right, so this is the example we're going to cover. So we've got, given that cos x minus y equals 3/5 and tan x times tan y equals 2, we want to find cos x plus y. So this one's, it's not too bad. We just need to apply all of the formulas. So I'll just go to my OneNote and we'll continue with this one. All right, so yeah, for this one here, I've also got the trig formulas here because we're going to use them. But we'll just start writing down sort of what we know. So firstly, we know that cos x minus y equals 3/5. So therefore, we know cos x minus y, according to the formula sheet here, is equal to cos x times cos y plus sin x times sin y. So we'll write that down, equals cos x cos y plus sin x times sin y. And they've told us that this is equal to 3/5. So we can say that's equal to 3 and 5. So this is sort of our first like simultaneous equation that we're going to use to solve for this one. All right, the second piece of information they've told us is that tan x times tan y is equal to 2. So, you know, tan x times tan y is also equal to sort of sin x on cos x times sin y on cos y, because we know that definition of tan. So tan x we can rewrite as like sin x on cos x. And tan y we can rewrite as sin y on cos y. So that's going to be equal to that on cos y. And we know that's equal to 2. All right, so we can times both sides by like cos x times cos y to give us sin x times sin y is equal to 2 times cos x cos y. Cos y. So this is sort of our second equation. All right, so now if we sub this second equation like into our first equation, so if we go sub that in, we should get, so it's going to be like cos x cos y plus our new value for sin x sin y, which is 2 cos x cos y. So we're actually going to get 3 cos x cos y in total. Cos x cos y is equal to 3/5. Right, so then solving this, we get cos x cos y is equal to 1/5. So this is like one of our sort of big solutions that we've got, and this is going to help us solve for cos x plus cos y. All right, so finally, using the formula for cos x plus cos y, which is here, we can rewrite it with in terms of cos x times cos y, which we just found. All right, so we know cos x plus y is equal to cos x times cos y minus sin x times sin y. Cool. And we already got an equation for sin x sin y, which is this equation 2 here. So we're going to sub that equation in there and see what we get. So we sub in equation 2. So then we get cos x times cos y minus 2 times cos x cos y is equivalent to cos x plus y. So then we can say minus cos x cos y is equal to cos x plus y. And above here, we just found cos x times cos y is equal to 1/5. So then, therefore, we can say the solution for this one is negative 1/5 is our answer. All right. So that's this one. So it's 3 marks, so it requires a bit of working. Yeah, so this is probably what I would show on the actual example. Just in general, like for this session, we're going to like overwork a lot of the examples. So for most of the questions, you're not required to write like as many lines as us, but we just want to be really clear with the question. Okay. So that's that example. So we'll keep going with our content. Okay, share. All right, so now we'll jump into area study 2. So in this area study, we're looking at algebra. So we're going to cover like solving over C, so over complex numbers. We're going to cover Demographers Theorem, or however you say it. So that's just the one with the equation in the circular function section. And then we're also going to cover partial fractions. So we've got like content and some exam questions for each one. Okay. So firstly, we just cover sort of a brief understanding of complex numbers. So we know complex numbers are based around I. So I is our imaginary number. Sorry, I'll just check. I'll just make sure we're all on the slides. Is that all good?
Yeah.
Cool.
Yeah.
Okay. So complex numbers are based around the imaginary number I, which is the square root of -1. So that's just like the main sort of theory for complex numbers. So we know we can write complex numbers in terms of like a real part and a imaginary part. So we write them in terms of like A plus BI. Okay. So in general, some handy sort of tools that we sort of might use are just like, we might use complex numbers for like polynomial division, also sum of squares. We've got that formula there. And then we also use the conjugate root theorem. So we use this in one of our examples that we've got coming up. So we know that if P of X, which is some polynomial, has all rational coefficients, so all of the coefficients are like real numbers, then we've got basically the function, if it has a root A plus BI, it also has a root A minus BI. So the roots sort of come in pairs for those ones. All right, so that's the general sort of content. So now we'll look at a couple of examples. So we've got this first example, which is solving over C. So that's just like a general example that uses the conjugate root theorem. And then we'll look at polar form just after that. All right. So solving over C. Okay, yeah, so as I said, this example does use the conjugate root theorem. So that theorem says that if all of the coefficients are rational, sort of like real, we can use the theorem. So we can see all of the other coefficients that like aren't defined as A are already sort of rational. And then it says A is a real constant, so therefore it's rational. So that means that we can use the conjugate root theorem. And the conjugate root theorem. So the conjugate root theorem just basically says that the solutions come in pairs. So if we've got Z equals 1 minus I is a solution, we know that Z equals 1 plus I is also a solution. So we've got if Z equals 1 minus I is a solution, therefore Z equals 1 plus I is also a solution. So that already gets us one of the other solutions, but we know there's going to be one other. And so basically we can write out this whole polynomial here in terms of 3 factors. So we've got Z minus 1 minus I. So Z minus 1 plus I is one of our factors, which comes from this solution. And then Z minus 1 minus I is our second factor, and that comes from this solution here. And we know that's only going to equal sort of a quadratic when we expand them out together. So we need one more linear factor to get our final solution. So we can write that as like Z minus B, which is some other solution. All right, so we know if we expand that out, that is going to be equal to our polynomial, which is Z cubed plus A Z squared plus 6Z plus A. Okay, so now we can just expand out the left side and we'll make that equal to the right side and equate some coefficients. All right, so if we expand out this left side, we're going to get, so Z squared minus Z minus IZ minus Z plus 1, plus 1 plus I Z minus I squared times Z minus B. So I've just expanded out the first 2 factors. So it's a bit tedious, but we sort of just have to do it. So once we've done this, we can sort of cancel some stuff out. So we can cancel these ones out. Basically all the I terms should cancel out. This one is going to be equal to negative 1 because I squared is -1. So that should just be equal to 1. Yeah, and then we can combine the other ones and basically we should be left with z squared minus 2 times z plus 2 times z minus b. And that's still equal to the right-hand side of the equation. All right, so once we've done that, we can continue to expand it out and expand it out with this other linear factor z minus b. So if we do that, we get that's equal to z cubed minus b z squared minus 2z squared plus 2bz plus 2z minus 2b. So we're going to want to sort of condense them down so that we collect like terms. Okay, so then that's going to be z cubed minus b plus 2 z squared plus 2b plus 2z minus 2b. Okay, so we can say that's equal to this polynomial here. So now we'll go about equating the coefficients. So for the z squared term, we can say minus b plus 2 is equal to a. So then we get b plus 2 equals a equals negative a, sorry, is sort of our first equation. Okay, and then from the constant term, we can say negative 2b equals a. So this is sort of our second equation. And now we can substitute that second equation for a back into the first equation. So we'll substitute 2 into equation 1. So then we get b plus 2 is negative 2b, so 2b. Therefore, solving this, we get b equals 2. And that's what we wanted to solve for, actually. So since we've solved for b, we can actually, that's going to be our final solution. Because if we solve that's equal to 0 using the null factor law, we get b is our solution. Okay, so we've got to actually answer the question that they asked us. So they asked us find all the other solutions. So we can say, therefore, the other solutions are, so z equals 2 and z equals 1 plus I was our other solution. So those are our two solutions for that one. Okay, yeah, as I said, this is probably like a bit of overworking, like you wouldn't have to write down every line for this one, but we just wanted to make sure you guys understand every step. Okay, so next we'll go into looking at like a bit of polar form. All right, so for this one, polar form. So polar form is just another way of expressing, so we can use it to express complex numbers. So these are sort of the equations for polar form. So if we've got a complex number, so like x plus yi, we can express it sort of as like r cis theta. So we've got theta is our angle from the positive x-axis sort of like up, and it satisfies the equation that tan x equals y on x. All right, so then, sorry, tan theta equals y on x. So therefore we can say like theta equals the inverse tan of y on x. All right, and then r is the magnitude, and r is such that, sorry, I'll reshare my slides. Yeah, so r is the magnitude and it's such that r equals the square root of x squared plus y squared. All right, and therefore we can say that like x plus yi is equal to r cis theta, and cis theta is just cos theta plus I sine theta. So we can write it like that. All right, so this is just covering Demographers Theorem. So it's just like an equation that makes this easier for us to do, like z to the power of n. So these are just like a couple of other sort of equations. So if we multiply two complex numbers, this equation up here can use, so we get r1 times r2 plus cis, and then we just add the angles. Division, we can make it easier for ourselves by just using this equation here. So we've got r1 over r2 cis theta 1 minus theta 2. And then finally, we've got Demographers Theorem. So this one's quite useful. So it's just when we're taking z to the power of n. So obviously that would be quite a big effort doing it by itself without this theorem. But we can say that's equal to r to the power of n times cis n theta. So it makes it much easier for ourselves. Okay, so in saying that, we'll get into an example. So we've just got this exam question. So it just wants us, for the first one, it wants us to find the integer values for which that complex number to the power of n is real. And then it wants us to find the integer value for which it's equal to ai, where a is the real number. All right, so I'll share my OneNote now. Okay, and I just included these little things from the exam report. They just tell us how sort of hard or easy the question was, basically, by showing us how the average cohort did. So in general, you have to remember that Spec is, of course, like quite a good cohort. They generally do pretty well. But these questions were quite hard because you can see the first one, we've got 61% got no marks, and then the second one, 74% got no marks. So it was like it was mainly just like a bit of a harder question to understand. But once you sort of get that, it's not as bad. All right. Okay, so for the first one, it just asks us to find the integer values of n for which this equation here is real. All right, so the first step of this one is to turn this complex number into like polar form, and then we're going to use the Demographers Theorem. All right, so firstly, we'll just turn like 3 minus root 3i into like r cis theta. So then we've got tan theta equals, according to the like equation, is equal to negative root 3 over 3, or negative 1 on root 3. So therefore, we can say theta is equal to like inverse tan of negative 1 on root 3. So therefore, it's equal to negative pi on 6. Okay, and then we can do like the same thing for r, just using the equation. So we get r is equal to the square root of 3 squared plus negative root 3 squared. So that's going to be equal to the square root of 12, or 2 times the square root of 3. Okay, so therefore we can say that the like complex number 3 minus root 3i is equal to, so r cis theta. So it's going to be 2 root 3 times cis, and theta is negative pi on 6. Okay, so now we can use Demographer Theorem. So we can say that to the power of n, so 3 minus root 3i to the power of n is equal to r to the power of n, so 2 root 3 to the power of n times cis n theta, basically. So cis n times theta, so negative n pi on 6. All right, and we know expanding this out, that's going to be equal to 2 root 3 to the power of n times cos theta plus I sine theta. Okay, so finally we've got it in that form, and it wants us to find the values of n for which it is real. Okay, so when it's real, we need to infer that means that this sine term here is equal to 0, because we can't have an I term. So therefore, if it's real, we know sine negative n pi on 6 is equal to 0. So using our like quadrants and stuff, we know sine is equal to 0, the pi units apart from 0. So therefore, we can say that negative n pi on 6 is equal to k times pi, when k is like an element of z, or k is an integer. So therefore, solving for this, we would get negative n equals 6k, which is just equivalent to n is equal to 6k. So it doesn't matter that it's like negative, it's just equivalent. And we have to say that k is elements of z, because we can only have like those certain integer values of k. But yeah, so that's the answer to that one. We've just got n is equal to 6k. So we found that just by equating the sine term to 0. All right, so this next question is quite similar. It's the same complex number, but it just wants us to equal to ai, so where a is equal to 0. So basically they're saying that the real part of this is equal to 0. So if the real part's equal to 0, we know that therefore this like cos minus n pi on 6 is equal to 0. So we've got cos negative n pi on 6 equals to 0. So we can do the same sort of thing. So we know cos is equal to 0 sort of like here and here. So it's like pi on 2 plus like pi units apart. All right. So therefore we can say that negative n pi on 6 is equal to pi on 2 plus kn. So where k is just an integer value. All right. So then solving for this again, we get negative n. If we just like divide everything by pi and times everything by 6, we get negative n is equal to 3 plus 6k. And we can sort of say the same thing for the other one. So we can also say that it doesn't matter, like the positive versus negative doesn't really matter because it's going to be like the same thing. So therefore we can say n is just equal to 6k plus 3, where n is elements of z. Sorry, where k is elements of z. So we must say this last part, we must say k is elements of z. Otherwise we won't get the mark. But yeah, that's going to be the answer for that one. Okay. So now we'll get on to the next question. Okay. All right. Share. All right. So now we'll be looking at partial fractions. So partial fractions, we really just need to remember like which sort of partial fractions corresponds to which denominator. So partial fractions just in general are used to sort of decompose rational functions into so sort of more easily understandable or easily integratable functions. So it's generally used for integration so that we can actually do it. Okay, so yeah, just in this example above, we've got this sort of more complicated function, x squared minus 3 on that denominator, and we can split it into that function on the right-hand side, which is much more easily integratable. Okay. So this is how we can convert like a factor to a partial fraction. So on the left side of this like equation, we've got the sorry, I'll just hopefully these slides are all good. So on the left side of this sort of what's it called? On the left side of this table, we've got the denominator. So if like ax plus b is the denominator, it just goes to a partial fraction a on ax plus b. And then if we've got ax plus b squared is our denominator, we have to split it into two partial fractions. So we've got a on ax plus b on ax plus b squared. So we have to split it into two. And then if we've got a factor of, so sort of like some quadratic that we can't factorize down, we have to split it into ax plus b on ax squared plus bx plus c. So those are the three sort of rules that we have to work out, that we have to remember for partial fractions. Okay, so again, we've just got one example here. So we just want to verify that that can be written as a partial fraction in this form here. Okay, so I'll share my OneNote. Okay. So firstly, we want to use our rules for partial fractions that I just had written down in that table. So we know the two factors below are this x squared term. So that's like, that is a squared term. So we're going to have to split it into those two partial fractions. And then we've also got this term here, which is sort of a quadratic term. So we're going to have to make that into like ax plus b. Okay, so we can rewrite like 5x cubed plus 12x plus 4 on x squared times x squared plus 4 as, so firstly we'll do like the x squared factors. So that's going to be like a on x squared plus b on x. We'll cover that one. And then lastly, we'll do the x squared plus 4 factor. So that's going to be like cx plus d on x squared plus 4. So we're going to be able to rewrite it like that. So now we just need to expand out sort of the right-hand side to get the numerator by like multiplying a, b, and cx plus d by sort of the rest of the sort of denominator that will make the denominators equal, if that makes sense. So then we can say like 5x cubed plus 12x plus 4 is equal to, so a is already on x squared, so then we need to times it by x squared plus 4. So a x squared plus 4 to make it sort of on that denominator, x squared times x squared plus 4. B, we need to times it by x and x squared plus 4. And then cx plus d, we need to multiply it by x squared. So that will be it. So now we can expand out the right-hand side of this equation and collect like terms again. So then we're going to get ax squared plus 4a plus bx cubed plus 4bx plus, where are we? Plus cx cubed plus dx squared. All right, and then when we collect like terms, we get b plus c x cubed plus a plus d x squared plus 4bx plus 4a. So now we can equate the coefficients. So we can say for the x cubed term, we can say b plus c is equal to 5. It's our first equation. And then for the x squared term, there's no x squared term in the numerator, so we can say a plus d equals 0 is our second equation. So therefore a equals negative d, sort of our solution for that one. And then from the x term, we can say 4b is equal to 12 and just solve that saying b is equal to 3. So from that, we can sub that back into equation 1 and get a solution for c. So then we get 3 plus c equals 5. So therefore c is equal to 2. And now finally, we can substitute that back into, now that we've got an equation for c. Sorry, we've got an equation for maybe, I think I'm missing one of them. Yeah, we can say from the constant that 4a is equal to 4 on the right-hand side, so therefore a equals 1. And then finally, we'll sub that sort of into equation 2. And we can say d is equal to negative 1. So we've got all the values, so now we just need to put them into their partial fractions up here. So we've got a is 1, so then that's going to be, so a fraction equals a is 1, so 1 on x squared plus b on x, so plus 3 on x, and then plus cx, so c is 2, 2x minus 1 is d on x squared plus 4, and that's equal to this here. So therefore we've sort of solved it. So that's, yeah, okay, so we've verified that that's equal to that. All right, so we'll get on to the next bit of content. Okay, what have we got here? So we've just got a video here just of the English masterclass that we've got coming up on Monday the 3rd of October. So it's just a quick video that I'll play for you guys. So let me know if there's any issues.
Hi, my name is Susan and I want to.
Okay, I'll just check. Okay.
Hi, my name's Susan and I'm one of the English tutors here at Skyline Hatch, and I'll be running the Ransom and the Queen Masterclass for comparative text response. This masterclass is essentially just a deep dive into Ransom and the Queen. So we'll kind of look at analysing each text separately, then we'll look at some really good examples of comparisons to answer different essay prompts, and we'll also look at some high scoring and low scoring essay responses to Ransom and the Queen comparative prompts. I hope to see you there.
Cool. Okay. Yeah, so that's just our English masterclass with Susan. She's really great. So if you guys want to check that out, I think Nan just shared a link in the chat. Oh, I don't want to play again. Okay, next. So next we've just got a bit of a break, but I think we're also going to answer some Q&A slides. So we'll just see if there's any questions that you guys have got, and then we'll get into the break. All right, so I'll just share the Mentimeter. Okay, so yeah, it doesn't look like we've got any questions. I'll just leave it up for a second, just in case you guys haven't been able to ask any questions, or if you want anything answered. But yeah. Yeah, just while we're waiting to see if we've got any questions. Oh, we've got some Q&A questions on Zoom, actually. We'll see what you guys have got. Oh, yeah. So can you send through the notes to the revision session afterwards, please? Yeah, that's no problem. So you guys will all have answers. Sorry, you'll all have access to like our OneNotes and everything, and also the slides. So you'll get access to everything. Yeah, and then the other question, just will we get access to the questions on the OneNote after the lesson? Yeah, definitely. So we'll share the OneNote with you guys. So don't worry about that. All right. Okay, so we've got a question. How do I improve my timing, especially on the long questions? For example, I was doing the 2021 Special Exam 1 yesterday, and one of the derivative questions took me 5+ minutes for 2 marks. Yeah, one of the last questions. Yeah, so I feel like that's a really common sort of issue that everyone has. Firstly, if it's one of the last questions, it's meant to take a while. It's meant to be a hard question. But of course, you don't want to like waste too much time because you're pushed for time. So I reckon, like, you've probably heard this a million times, but I'd probably just say practice like as much as you can to try and improve. You don't need to always write down like every single line of working. You can try and sort of skip stuff. They're only looking for certain sort of key points, so you don't need to write down like absolutely everything. Yeah, and then I'll just say like sort of get maybe try and get quicker at like knowing the formulas and stuff. Try not to rely on your notes or your formula sheet. Like that might help you get a bit quicker as well. But like Nyang or Justine, do you guys have any advice?
I guess breaking down why you're losing time would be useful. If if in the first few minutes you just, I won't say waste time, but you go into like, oh no, what's the formula to apply, or what do I do there? Then that's something that can be specifically targeted and practiced.
Yeah, no, exactly. That's a good point. Does anyone else have any like advice on timing or anything?
I recommend, because I remember my first 2 exams I took a quiet bit of time to go through the questions, but as I do more of practice exams, it gets better. So
yeah, no, exactly. Yeah, no, that's a good point. It's always gonna, like, I didn't even time my first exams or anything. I would just try and do them and finish the questions. Yeah, but I would say worry like a little bit more about the timing as it gets closer to the exam, but you'll like naturally get better. And also if it's the last question, they do like make the last questions much harder or much more time consuming than the rest of them. Okay, so that one's marked. I think we've got one more. So do you have any tips for specifically the kinematics, statics, and dynamics kind of questions? Okay, yeah, those are sort of like my favorite type of questions, just because they're more like practical. But what would I say would be tips? Well, obviously, like this is pretty obvious tip, but just try and do like a lot of practice exam questions, like specifically on them, if you're struggling more with those type of questions. Otherwise, yeah, like sort of try and like have a good understanding about how it like actually works, like not just the formulas, but about like how we can convert like acceleration to velocity, like etc., stuff like that. So if you've got a good understanding of how it works, you'll probably find it like a little bit easier. But yeah, Nang, do you have any advice for that one?
Oh, I'd say
this is mostly for kinematics, but if you try and gather everything you have, let's say if in your question you have Q, A, and S, you can try and like point it out and then just look at any equations that has those. And I think it's saves a bit of time.
Yeah. Yeah, no, that's a good idea. So you just sort of have your formula sheet sort of next to you and always just write down what you know at the start of the question. And then that should sort of lead you somewhere. All right. So last question. So is it possible to get the slides for this, please? Yeah. Are they able to get the slides like now, if they want them? Or like, I think like maybe a link might have been sent to you guys. But yeah, we'll get them to you ASAP otherwise. Okay, so it looks like the last one. Yeah, so I think Yang just sent them the link to the slides for you guys. So if you want them now, feel free to go and get them. So we'll just go on from the Q&A Zoom. So do you know any useful CAS tricks or UDFS that we should be using for the special exams? So CAS tricks. I don't know about tricks. Like, I'm not sure if you guys actually still, I feel like some people have different CASs. I'm not sure if you still have the same one as me. But it's not so much as a trick, but just like opening a new document for every extended response question is quite helpful. So on my one's sort of the old one, but you can go like doc 4.1 and open like a completely new document. And that allows you to sort of go back to your old documents and you'll still have all of the equations and all of the functions defined. So it allows you like if you have any time left over, you can go straight back to it and like not worry about defining the functions again. And yeah, I would say that it's like a little bit of not so much as a trick, but just something handy to do. But does anyone else in the panel have any like tricks or anything?
I think there are a lot of tricks on YouTube that you can try and look for it. I remember like I find out that there are so many ways. Like I can just put how to find like for complex number, find solution and put it in a calculator right before the exam. But I think you guys should try and like go through YouTube and search out for your class specifically, like any tricks that's out there.
Yeah, no, exactly. Just because, yeah, the new CASs, I don't even know. I'm sure your teachers are all good, but just because they changed it up, like maybe they don't know, or maybe you guys are just a little bit unfamiliar with it. But if you go onto a website, I'm sure that would help. Oh yeah, someone in the chat says they found a website called Scripted Math, and they've got a lot of good functions. So yeah, I'll check that out. But it's really important to be able to use the CAS well, especially, well, obviously in exam 2. Yeah, all right. Cool. So I think we have the break till like 11:05. So I'll just give you guys like 5 minutes more for like an actual break, and then we'll come back at 11:05. Yeah, that's like good with the timing, right, guys? All right, I think that's all good. Okay. Okay, so hopefully everything's working again, but I think we might just come back now. Okay, whoops. So we've just got another video for you guys just before we start. So I'll just check that everything's working. But yeah, so this is just like a video about UBS, who's like our partner for this like exam revision series. So I'll just play that for you guys.
I think one piece of advice I would definitely give someone who is in year 12 studying their final exams would be to try hard. I think I've heard a lot of rhetoric in the past couple of years where people are saying that, oh, you know, it's not the end of the world, it doesn't really matter what score you get, and they're right in saying that it's not the end of the world, but I think anyone would really regret not trying hard to begin with. So just apply yourself, don't leave things to the last minute, and I think I said before, just do a lot of practice exams. That's really helpful.
Okay. Yeah, so thanks to UBS for sharing that. Okay, so we'll get into the next little bit of content. So now we've got area study 3. Yeah, okay, so this one we've got implicit differentiation. We're going to look at like U substitution for calculus, and then arc length formulas and questions, as well as solids of revolution, differential equations, and then finally so sort of equations for like acceleration. All right, so I've got a lot in this sort of area study because calculus is like one of the biggest ones. But yeah, we've got like a bunch of exam questions that we'll be going over for this one. Okay, so firstly, we're going to look at implicit differentiation. For implicit differentiation, it's just like another way we can differentiate stuff. So like usually we just differentiate sort of over one variable. So we've got like y equals some function of x, but with implicit differentiation, we can sort of use the chain rule to differentiate functions in terms of like y and x. So basically, like we've got the chain rule here, du dx equals du dy times dy dx. And then we can use the chain rule and say that the derivative of y with respect to x is equal to, so it's going to be du dy times dy dx. So du dy, we can just leave it there. Du dy, we can differentiate y sort of squared in this case with respect to y easily, and that's just going to be equal to 2y. But then we just have to leave dy dx there, sort of. So we've just basically used the chain rule, and it means that we just have to express the derivative of y squared with respect to x as 2y times dy dx. So we're going to leave dy dx in that equation. Okay, so next we're going to look at this exam question. So we've got an implicit differentiation exam question. So this one is quite hard, or it's like quite a lot of working, which we can see because it's 5 whole marks. So it requires quite a lot of working. I will probably overwork it as usual, just so I make sure we've explained everything. But yeah, just like the main parts of it is we want to use implicit differentiation to differentiate the equation up here, because we've got it in terms of like x and y, and we can't really separate them out very well. And then we want to give our answer in that form there. So we're not going to worry too much about the form at the start. We're just going to sort of solve it. And then if we get the right answer, it should sort of sort into that form. But yeah, as I said, it's like quite a hard one. It took me a while to work it out because I kept on making mistakes, just because it's like quite a lot of sort of annoying working. But yeah. All right, just make sure my OneNote's shared. Okay. So again, I just included the sort of marking scheme for it, like how the cohort went. So we can see it's 5 whole marks, so it's sort of hard to get all of them. So probably like a bunch of people didn't have time to get up to it because it's like the last question. So like 12% got 0, but we can see it's sort of a bit of a spread for the rest of it. So you can see that the last mark is a bit hard to get because only 18% of people got it. So yeah, this would have been sort of the result of it being the last question, and also the fact that it's just sort of a hard question. Okay, so firstly, it just wants us to find dy dx at that point here on the curve defined by this equation here. So firstly, we're going to just section it out into steps. So firstly, we'll find the derivative of that equation, then we'll sub it in, and then we'll try and get it in that form. Okay, so using implicit differentiation, we'll try and differentiate the whole equation with respect to x. So then we get d on dx of sine x squared plus d on dx of cos y squared equals, and then d on dx of 3 root 2 on pi xy. So this part here also makes it a bit difficult because we can see they're not separated out. So we're actually going to have to use the product rule on this part here because we've got x and y in there. All right, so the left-hand side's not too bad. We just used our implicit differentiation formulas. So firstly, the derivative of sine x squared is going to be like 2x times sine x squared. And then the derivative of cos y squared, using our implicit differentiation formula from the previous slide, it's going to be, so the derivative with respect to y, which is going to be minus 2y times, oh, sorry, this is going to be cos, this one. So it's going to be minus 2y times sine y squared. So that's just the derivative with respect to y. But we have to multiply that by dy dx for the chain rule to be satisfied. So for it to be the derivative of cos y squared with respect to x. All right, and then that's going to be the derivative of this one with respect to x. So I'll just do that down a bit lower because it requires a bit of working. So we're going to have to use the product rule to solve this here. So d on dx of 3 root 2 on pi of x times y. Okay, so this here requires the product rule. Obviously, you wouldn't have to write product rule or anything. I'm just doing it so I can like better explain it. Product rule. All right, so for the product rule, we've got it's like equal to u times dv dx plus y times du dx. So I'll just define them. So I've got u equals 3 root 2 on pi times x. So therefore we get du dx is equal to just 3 root 2 on pi if we differentiate that with respect to x. Right, and then I've got v is just equal to y, and then we define dv dx. So we want it with respect to x. So therefore it's going to be equal to 1, which is the derivative with respect to y. So 1 times dy dx. So we've sort of just done a little implicit differentiation here. All right. So now that we've done that, we can say the derivative is equal to sort of like y times du dx plus u times dv dx. Okay, so it's going to be those ones plus those ones. Okay, so then we get d on dx of the right-hand side is equal to 3 root 2 on pi times y plus, because it's the product rule, so plus 3 root 2 on x times d dy dx. 3 root 2 on x times, 3 root 2 on pi times x times dy dx. Okay, so that's the right-hand side of the equation. So therefore we can say like all of this is equal to this, and because that was just the right-hand side. So we've got 2x cos x squared minus 2y sine y squared is equal to 3 root 2 on pi y plus 3 root 2 on pi x dy dx. Okay, so you can see it's even been like a lot of working so far, but we've still got quite a bit to go because we need to like solve for dy dx and then sub it in. All right, so we need to collect dy dx on one side and then just sort of solve for it by itself. This where has the dy dx on this side? Sorry, this has dy dx. Okay, so collecting like dy dx terms on the right and other terms on the left, we get 2x cos x squared minus 3 root 2 on pi y is equal to, so dy dx times 3 root 2 on pi x, and then plus 2y sine y squared from here. Okay, so then just solving for dy dx, we just divide both sides by the stuff in the brackets on the right-hand side. So it's going to be 2x cos x squared minus 3 root 2 on pi y over 3 root 2 on pi x plus 2y sine y squared. Okay, cool. So finally, to simplify this down, we just times everything by sort of pi on pi, so that it'll be like 2 pi x cos x squared minus 3 root 2 y on 3 root 2 x plus 2 pi y sine y squared. Okay, so that's just going to simplify it down a little bit for us. So now finally we can sub in our points. So that's going to be, we're subbing in root pi on 6. So x equals root pi on 6 and y equals root pi on 3. So we're going to find dy dx when x equals root pi on 6 and y equals root pi on 3. All right, so we'll sub that in. So it's going to be like 2 pi times root pi on 6 times cos root pi on 6 squared. So just cos pi on 6. And then that it's going to be that minus 3 root 2 times y, which is root pi on 3, divided by 3 root 2 times root pi on 6 plus 2 pi times y times root pi on 3 times sine y squared, which is just pi on 3. Okay, so now it just requires a lot of sort of tedious simplification and stuff. So we know cos pi on 6 is just equal to root 3 on 2 and sine pi on 3 is equal to the same thing. So it's going to be 2 pi times root pi on root 6 times root 3 on 2 minus 3 root 2 times root pi on root 3. Okay, and then on the bottom, so it'll just be the same, root pi on 6. We'll just separate it out so we can simplify it better. Plus 2 pi root pi on root 3 times root 3 on 2. Okay, so now we'll sort of start simplifying it, but I'm just going to split it into numerator and denominator so it makes it a bit easier for us. So numerator is going to be like 2 pi instead of all of that. So it's going to be 2 pi times root pi over root 6 times root 3 on 2 minus 3 root 2 times root pi on root 3. Okay, so we'll start simplifying. So firstly for this one, we can swap out those sort of 2's. Then we can simplify this by making that root 2. So that's all we can do for that. And now we can cancel out these 3's. And then we're left with pi root pi on root 2 minus root 3 times root 2 times root pi. All right, and then if we times all of that by root 2 on 2, we're finally going to get pi times root pi minus 2 root 3 pi on 2, root 3 root pi on 2. Okay, so then finally we can separate that out into root pi on root 2 times pi minus 2 root 3. Okay, all right, so finally denominator. We can do sort of the same thing. So we're going to cancel that out. So I'll just sort of quickly write it out. I know it's like a bit tedious. Pi on root 6, which is sort of going to be root 3 times root 2 plus 2 pi times root pi over root 3 times root 3 on 2. Okay, so we'll go about cancelling stuff out again. So those can all be cancelled. Those can be cancelled. That will turn into root 3. Then finally we get root 3 root pi plus pi root pi. And that's going to be equal to, root pi times root 3 plus pi. Okay, so finally putting the numerator on the denominator, we get that's equal to, so the whole fraction is equal to root pi on root 2, which is the numerator, times pi minus 2 root 3, divided by root pi times root 3 plus pi. Okay, and then simplifying it down and getting into the form that they wanted, it's going to be pi minus 2 root 3 on root 2 times root 3 plus pi. Okay, so you can see, in my opinion, it's a horrible question because it's so much working, but finally we did get it down into this form. And obviously it is 5 marks, so it's a lot of working, but obviously you don't have to write down all of those lines that I did. It was like overworking. But yeah, as long as you get sort of the main points, and yeah, you can see that we've got in the form they wanted. So they wanted like pi minus a root b on root a times pi plus root b. So we've got that all in there for them. but yeah, so you can see, don't worry too much about the form. As long as you sort of get to the answer, you should be able to put it in the form that you wanted. But yeah, okay. So now that we're done with that question, we'll get on to some more content. Okay. All right, so that was implicit differentiation, and now we'll just move on to use substitution. So we're moving to integration here. So a useful tool that we often use in Spec is the use substitution. Oh, my camera's finally working. Oh, no, it's not. Okay, anyway, a useful tool that we often use in Spec is the use substitution. So we have to choose sort of an appropriate substitution to make as u, so that we can integrate in an integral that we might otherwise not be able to solve. All right, so the best way to revise it is to sort of just jump right in. And just a note is that we don't want to rush the substitution too much. So we want to write down all the steps and just go through it sort of slowly and steadily. So yeah. Okay, so I'll share, and this one is like a nice, easier question than the last one, so it's not so much working. Okay, so we can see it's 3 marks, so we want to hit a few sort of key things. So firstly for this one, straight off the bat, we can see that it's a bit of a complicated integral, and it's got a cos term and a sine term. So we're thinking, and the cos term squared. So straight away, we should be thinking we should be able to use a use substitution for this one. And we should usually we just make the use substitution the function that is sort of more complicated. So in this case, the cos function is squared. So we'll make u equal to cos 2x. All right, so firstly, we can say let u equal cos 2x. Therefore, we've got du dx is equal to -2 times sine 2x. Perfect. And you can see sine 2x is in there, so it's looking good. And then now we just want to solve for du by itself, because we're going to be substituting du into the equation, sort of. We'll get there in a second. So we can say du is -2 sine 2x times dx. All right. So this here, we're looking to put that in here so that we can substitute that for du and make it much more simple. Okay, so now I'll rewrite this equation here, but I'll try and put this in it. Okay, so I can rewrite that equation by making it equal to I'll put -1/2 out the front, so I can put -2 inside the integral. And then we've got pi on 2, 3 pi on 4 cos squared 2x. And then that's going to be times by -2 sine 2x dx. Okay, so you can see, because I've got this -1/2 out the front, that -2 is fine to be in there because it's exactly the same integral. But now that we've got that -2 sine 2x dx, this whole term can be replaced by du. Okay, and also obviously cos 2x can be replaced by u as well. So then we'll get, and we need to leave this as x equals pi on 2 because we don't have them in terms of u yet, and x equals 3 pi on 4. And then cos squared, I'll keep the -1/2 out the front, but cos 2x squared can be turned into u squared, and that whole term sort of underlined in red, as I said, will be converted to just du. So we can see it's so much simpler already. Okay, so now we just need to deal with the endpoints. So we've got x equals pi on 2 and x equals 3 pi on 4. So we need to turn them into u values, and we can turn them into u values by this equation here. So we've got u equals cos 2x. So we'll try for pi on 2 first. So then it's going to be u equals cos 2 times pi on 2, which is just cos pi. So that's going to be equal to -1. All right, and then we'll do the same thing for x equals 3 pi and 4. So u equals cos 2 times 3 pi and 4, which is just 3 pi and 2. And then that's going to be equal to 0. So those are our new endpoints. So then we can rewrite this as -1/2 times, so the integral is going to be 0 to -1, u squared du. Perfect. So that now that's a much, much easier integral to solve. So we'll go about doing that. So 0, 1, u to the power of 3 on 3, And then we'll sub in, -1, we'll sub in our values. So that's going to be -1/2 times -1 to the power of 3 on 3 minus 0. Yeah. Oh, wait, let me just make sure that I put them in the right. Yeah. Okay. Sorry. I put them in the wrong spot. It was pi and 2 was -1, and then the other one was 0. So I put them in the wrong spot, but I've just fixed that up now. So 0, -1. So it's actually going to be 0 cubed minus -1 cubed on 3. Okay. So if we expand this out, it's going to be -1/2 times 0 minus a third. So that's going to be times a third because the negative signs will cancel out. So it should be equal to -1/6. So that's our final value for that one for the integral. So we've got the answer is -1/6. So yeah, that's just how you use the U substitution. But yeah, I'd say one of the key points that we want to look out for is just the endpoints, because I know I sometimes forget to change them around. Okay. Perfect. So we'll get on to the next little bit. Okay. So now that we've done the U substitution, we'll look at some other applications of integral calculus. Okay. So we want to look at arc length. So there's a couple of formulas for arc length. So we've got L equals. Yeah, so L equals from like x1 to x2 of the square root of 1 plus f dash x squared. So that's for like a regular function. And then we've also got L equals, so from t1 to t2 of x dash t squared plus y dash t squared. So that's like the parametric representation. So we can use one or the other based on sort of the equation that we've got. And then we've also got volumes of solids of revolution formulas. So about the y-axis, it's going to be this formula, and about the x-axis, it's that formula there. And basically, it's just equal to pi r squared, basically. So if it's about the y-axis, we're sort of flipping it around the y-axis. So therefore, if you think about it, the radius, this is the opposite to the picture that's there as well. But if you think about it, the radius is going to be our sort of x value because it's like the x length. So therefore, the integral would sort of just like sum this up over a certain domain, but it's basically equal to pi r squared because x is sort of our r value. Also, don't worry if this goes over your head. This is just how I think about it, but really we're just using the equations. And then also for the x-axis, we've got sort of a similar thing, but we're just flipping it around the x-axis. So this is the same as the picture there. So in this case, it's like sort of pi r squared again. But r is our y value because we can see the radius like in this picture is equal to the y value or like the function value. So if we just go pi times that squared over the domain of a to b, that's going to be equal to the volume of the solid. So that's sort of why the functions are like that. But otherwise we can just remember those functions. So about the y and the x-axis. Okay, so we've got a couple of examples now. So firstly, it's just like an arc length example. And then I think the next one is a solids of revolutions example. So we'll just go over both of those ones. All right. Share. Okay, so we start up with arc length. So we're going to be using one of the formulas from the other one, but this one is like a parametric function. So we're going to be using that parametric equation. So we've got x equals cos 2 theta minus 3 and y equals sine 2 theta plus 1. So this first question is asking us to sort of write down the definite integral in terms of theta that gives the arc length from theta equals 0 to theta equals pi for the curve defined parametrically as shown. Okay, so yeah, it's just asking us to use the arc length formula, but this specific question isn't asking us to evaluate it yet. It's just asking us to write down the integral. All right, so just get this up. So we know that the general sort of form that we're looking for is like L equals, so from theta 1 to theta 2 of the square root of, so x dash theta squared plus y dash theta squared d theta. So this is the formula that we're looking for. We just need to find x dash theta, y dash theta, and then we've already got like theta 1 and theta 2. Okay, so x dash theta, just according to our derivative laws, is going to be -2 sine 2 theta. Okay, and then y dash theta is going to be equal to 2 cos 2 theta. Cool, okay. Now that we've got that, and then we've also got, x1 is equal to 0 and theta 2 is equal to pi. So now we'll substitute all of those things in. So we've got 0 to pi of the square root of -2 sine 2 theta squared plus 2 cos 2 theta squared d theta. All right, so now we'll just go about simplifying that a little bit. So it's still going to be 0 to pi, but if we square it, it's going to be like 4 sine squared 2 theta plus 4 cos squared 2 theta. So if we take out the 4, it's going to be like 4 times sine 2 theta squared plus 4 times cos squared 2 theta d theta. All right, and then we know sine squared plus cos squared is equal to 1. So it's actually going to be equal to, 0 to pi of like root 4 times 1, which is just 2. So this is our final sort of integral for that one. All right, so that makes it so much easier to solve for question B, which is just find the length of this arc. So it just wants us to integrate that like equation. So 0 to pi of 2 d theta, that's going to be 0 pi 2 theta. So therefore, it's going to be equal to 2 pi minus 0, or 2 pi units. They haven't really given us the units, but we should just write units because it's technically like a length. So that's the answer for that one. Okay. Oh, actually, the next question was sort of straight up. So now that we've done arc length, we can go to solids of revolution. And we know the formulas were just on that slide before. So we'll jump straight into this question. Okay, so for this one, we want to find the volume of the solid of revolution formed when the graph of y equals root 1 plus 2x over root 1 plus x squared is rotated about the x-axis over that interval. All right, so you wouldn't need to write this. Sorry, you wouldn't need to draw this, but I'll just sort of draw what we're doing. Also, it could be a good idea to just draw just to get your head around it. So we've got this function. It could look like anything. I'll just draw like a random squiggle, but it's from like 0 to 1. So I'll just draw something random. So basically it's that function, and we want to rotate it about the x-axis. So if we sort of like flip it like that and get like the symmetrical, we're basically trying to find the volume of that. Okay. So if we're using the formula, obviously, but if we think about it, we want it to be like pi r squared from 0 to 1, and the radius in this case is going to be sort of these values here. So the radius is going to be the y value. So therefore, the volume is going to be from 0 to 1, pi times from 0 to 1 of sort of r squared dx. Cool. Okay, so now we'll replace y squared with this side of the equation, y squared. So therefore, it's going to be pi, the integral from 0 to 1 of root 1 plus 2x on 1 plus x squared squared. So that's just going to be 1 plus 2x on 1 plus x squared dx. All right, so now we're just going to work out that integral. Okay, so we'll section it out. We'll section into like 1 on 1 plus x squared plus 2x on 1 plus x squared. So that's going to be pi times 0 to 1 of 1 on 1 plus x squared dx. And then the same thing, but with 2x on 1 plus x squared. So we've just separated out our fractions there. All right, so using the formula sheet here, or just your knowledge if you sort of remember it, but we can say that the integral of 1 on 1 plus x squared is going to be, we're going to use this one here to find it. So a is sort of 1 in this situation. So the derivative of that one is going to be inverse tan of x. Okay, so then that's going to be 0 to 1 of inverse tan of x. And then this one here, we've got 2x on 1 plus x squared. So to work that one out, we can use, it's actually not, sort of not on here. Yeah, it's sort of not on here, but it's going to be the integral of like log, because we know that if we integrate log e 1 plus x squared, we're going to get 2x on the top of the fraction and 1 plus x squared on the bottom. So we just need to recognize that. So the integral is going to be 0 to 1 of log e 1 plus x squared. So all of that still times by pi. So now we can evaluate it. So it's going to be pi. So inverse tan of 1 minus inverse tan of 0 plus log e of 1 plus 1 squared. So log e 2 minus log e 1 plus 0. So log e 1. Okay. So we know inverse tan of 1 is equal to pi on 4, and inverse tan of 0 is just 0. Log e2 we'll leave it, and log e1 is 0. So then this is going to be pi times pi on 4 plus log e2. Cool, and we can expand it to like pi squared on 4 plus pi times log e2, but this is a perfectly fine way to leave it. And yeah, just don't do too much work if it's not required. Which I have done on all of these questions, of course. But yeah, try and like make it sort of easy for yourselves. Okay. So we'll keep going with that, with the next sort of bit of content now. Okay. So hopefully it's all good. All right. So now we've done solids of revolutions. We're going to look at differential equations. All right. So this is the last sort of thing that we're going to cover in Area Study 3. So yeah, for the sake of time, we won't like be covering all of the theory and everything. We'll try and do some worked examples instead. So for the first example, it's quite a difficult one. Again, it's like quite a lot of working. But we think it is a good one just because of like the theory behind it. So we'll be going through that one. And then the second example, we'll be using this identity A equals V dx. Sorry, V dv dx. Yeah, so that's just like one of the kinematics equations for A. So that's sort of like a kinematics, kinematics question. But the first one that we're focusing on is just a regular differential equation one. Okay, so this is the first question we're going to be covering. So it's question 10 from the 2016 exam. So it's an exam 1 question. It's the last question because it's question 10, and it's 5 marks. So it's a pretty big question. But we'll go over it sort of step by step. And as I said, it's a bit of a hard one as well. So it will take us a little bit. Sorry, you can't see the question. I'll just reshare. Okay, hopefully that's all good. But you'll see it on my OneNote in a second anyway. And then the second question is just sort of a regular kinematics question, so it's a bit easier. All right. Okay, so I'll share the question. So the first one we're going to cover is this differential equations one. So as I said, it's a bit of a hard one, and we can see that by sort of the marking scheme. So we've got 20% of people got 0. Again, it's the last question, so that might have been because they didn't really get a chance to start it. Also, it's just like generally a hard question. And we can see this one's like a bit more spread to the lower marks as well. So not as many people got like 4 or 5 marks as the like last questions that we've been going over. But yeah, we'll just get straight into it. Okay, so for this one, the first step is just to separate it out. So we want the like x components on the x side with dx, and we want the y components on the y side with dy. So basically, we're going to do a bit of sort of cross multiplication. So we're going to times both sides by 2 minus y, and we're going to times both sides by like sort of dx and divide it by root 2 minus x. Okay, so yeah. Basically, if we do that cross multiplication, we're going to get 2 minus y dy is equal to 1 on root 2 minus x squared dx. Okay, so we've got it in that form now, so we can go on and sort of integrate it. So if we integrate this, we've got 2 minus y dy, so we're integrating both sides, equals 1 on root 2 minus x squared dx. Cool. Okay. So the left side is quite easy to integrate. We've just got 2y minus y squared on 2 equals, and then on the other side, apologies, I don't actually have the formula sheet down here, but basically it's going to be inverse sine of x on root 2. So we're using that, that integration formula on the formula sheet for the inverse of sine. So you guys can have a look at that if you want, but it's just going to be that, and then we're going to leave plus c on sort of this side. So technically it'll sort of have a plus c on both sides, but it's just a constant, so we can combine it just on one side. So we just leave it there. All right, so now we're going to substitute early just so we can make it easier for ourselves and not have like a c in the rest of the sort of working and everything. So we know that when x equals 1, y equals 0. So then we'll substitute this in. So on the left side, we'll just have like 0 minus 0 squared, blah, blah, blah. So we'll just have 0. And then on the right-hand side, we know x is equal to 1 when y is 0. So we've got 0 equals inverse sine of 1 on root 2 plus c. Okay, so we know the inverse sine of 1 on root 2 is equal to pi and 4. So then therefore we get c is equal to negative pi and 4. Perfect. Okay, so we'll sub that back in. So then we get 2y minus y squared on 2 is equal to, inverse sine x on root 2. Oh, that was badly written. Inverse sine x on root 2 plus c, it's minus pi and 4. All right, so now we're going to solve for y. So this looks a bit like confusing, like we can't really get y by itself, but basically we're going to have to complete the square on the left-hand side to get y by itself, and then we're going to like sort of square root everything. So firstly, we'll just times everything by 2 to make it simpler for ourselves. So then actually we'll times everything by -2 just to make it really easy. So then we get y squared, so just times by -2. So then we get y squared minus 4y equals, so -2 inverse sine of x on root 2 plus pi and 2 is what we get. Cool, okay. And now we want to complete the square on the left-hand side. So you can see if we do, if we complete the square to make it like y minus 2 squared, we're going to get, so y squared minus 4y plus 4 minus 4 is going to be equal to just like y minus 2 squared minus 4. So we need to remember that minus 4 is equal to -2. So -2 times inverse sine x on root 2, etc. Okay. So now we get like y minus 2 by itself. So I'll just like do these steps in one. So then we get y minus 2 equals plus or minus the square root of all of that plus 4, because we needed to remove that 4 sort of over here. So plus or minus the square root of inverse sine, -2 inverse sine x on root 2 plus pi on 2 plus 4. Okay, so this here is like a bit of an important step. Here basically we need to choose one. We can't leave it as plus or minus because that's like 2 equations, and we always need to choose one because we need one equation for y. So we have to make our selection. So it's a bit difficult here. We need to like really think about what we've got. So basically we go back to our initial condition. So we know when x equals 1, y equals 0. And we always know that the square root of something must always be positive. So we also know root whatever must be positive. Okay. So if we sort of substituted these values in, if we substituted y equals 0, we're going to get -2 equals plus or minus the square root of something. And we know this is a positive value. Yeah, the square root of something. And that square root is going to be positive. Okay, so if we substituted that in, we know -2 has to be a negative value. So therefore we have to choose the negative root, not the positive root. So because of that initial condition, we have to choose the -1. So we know the root must be negative. The root must be negative. Be negative. Okay, so then we can say, therefore y equals, so we'll like put the 2 on the right hand side as well. So y equals 2 minus the square root of negative 2 inverse sine of x on root 2 plus pi on 2 plus 4. And we say that that is because we reject the like positive root, because sort of 2 minus that sum value, 2 minus the square root value has to be equal to 0. Root blah, blah, blah has to be equal to 0 when x equals 1. All right, so basically basically this here is our answer. So it's quite a hard one to reject because it's not the easiest sort of method. But basically you have to reject it because of that initial condition. So we know that y equals 0 when x equals 1, and the square root of something always has to be positive. So therefore, sort of in this step here, we have to choose that negative root. All right, so hopefully you guys are all good with that. I'm happy to like go over stuff like this again if you have any questions, but otherwise we'll go on to the next question. So I just check if there's anything got left on the slides. Okay, so yeah, hopefully you guys can see that, but this is our next question. So we've got a question where we're using a equals v dv dx. So there's a couple of equations for acceleration. I think they're in the formula sheet, but I think we've got like a equals the second derivative of like x with respect to t, a equals dv dx. I think there's like another one, a equals dv dt, etc. So we have to pick the formula for a that makes sense in the situation to work out the question. So in this case, we're using like a equals v dx because like I wrote it down there, but we'll work out that it's the only one that sort of makes sense that we can use to solve this one. All right, so we'll go back to the OneNote. Okay. All right, so for this question, we've got the acceleration, a meters per second squared, of a body moving in a straight line in terms of the velocity is given by this equation. So we've got a equals 4v squared. All right, so now they've given us an initial condition. So they say given that v equals e when x equals 1, so x being the position, v being the velocity. Yes, okay, where x equals the displacement in meters. We find the velocity of the body when x equals 2. Find the velocity of the body when x equals 2. All right, so firstly, we're just going to work out an equation for v in terms of x, and then we want to find the velocity when x equals 2. So basically, we have to use this condition a equals v times dv dx because our end goal is to find v when x equals 2. So therefore, we sort of need x net. And we're given an equation for a in terms of b. So basically, this is the only one that we can use. All right, so we know a equals v dv dx. And also from the equation, we know acceleration in this case is equal to 4 times v squared. All right, so just solving this equation, we can divide both sides by v. So then we get dv on dx is equal to 4v. All right, so now we'll do sort of the same thing as we did in the last question, and we'll separate it out so that the v component's on the v side and the x component's on the x side. So if we times both sides by dx, we get dv equals 4v dx. So we can't really do this very easily, so we need the v on the v side. So we can divide both sides now by 4v. So then we get 1 on 4v. dv is 1 times dx. And therefore, we can integrate both sides. So we integrate that side and integrate this side. Cool. Okay, so now we're integrating both sides. So integrating the left side, it's going to be a log. So therefore, we're going to get 1 on 4 log e v plus c. So 1 on 4 log e v plus c. And on the right-hand side, we're just going to get is equal to x. All right, and again, There's sort of a plus c on both sides if we integrate this, but it's just a constant, so we can separate it down into one term. All right, so now that we've got the c, we'll sub in our initial condition to solve for this. So we know that when v equals e, x is equal to 1. So therefore, we've got like 1/4 log e of e plus c is equal to 1. So we know log e is equal to 1. So therefore, we've got 1/4 plus c equals 1. So then c equals 3/4. Cool, okay. So now we'll rewrite the equation for like x in this case. So we've got x is equal to 1/4 log e v plus c, plus 3/4 now, which is c. Okay. So they want us to find the velocity when x equals 2. So this is an equation for x, but we really want an equation for v. So we'll swap it around. So firstly, we'll times both sides by 4. So then we get 4 equals log ev plus 4x. We'll minus 3 from both sides. So log ev equals 4x minus 3. And then we'll swap from log form to exponential form. So swapping forms, we get v is equal to e to the power of the right-hand side. So e to the power of 4x minus 3. Okay, so now that we've done this, we can finally sub in our condition, which is x equals 2. So v when x equals 2 is equal to e to the power of 4 times 2 minus 3. So it's equal to e to the power of 5. We need to include units as well. So it's going to be e to the power of 5 meters per second because it's a velocity. All right, cool. So we've answered that question now. But yeah, this is just like sort of an example of a typical kinematics sort of question. But yeah, so we need to pick the right equation for a is like the main point of this one. And then we use like integration as usual. All right, let's see what we've got next. Okay, so that was a equals. So now we've got a little break time. How are you doing for time? I think we're going all right. So I think we'll go into like a little bit of Q&A again, and then we'll give you guys a little bit of a break as well, so you can go like get a drink and stuff. Okay, so I'll swap to the Q&A slide, and we'll do a little bit of that. Okay, so hopefully you guys can see my Mentimeter now. But yeah, again, if you guys have any questions, please log into Mentimeter and like let us know what you're thinking. But otherwise, we'll take a little bit of a break. Okay. Yeah, does anyone else on the panel want to say anything if we don't have any questions? Or are we all good?
No, I think we're all good.
Okay, perfect. So sorry, I don't have the run sheet time, but what's the plan for the break? Are we ending at like 12:05 and then we're on? Okay, cool. So it looks like you guys don't have any questions. If you do, feel free to put them in the Menti chat. But otherwise, we'll just take a little 10-minute break here. So feel free to go get a drink of water and have a little break. So we'll come back at 12:05. Okay. All right, so we'll start again now. So I think we have just a couple of area studies left, so we're almost done. So I'll take the next one and then we'll be taking probability, as I said at the start. So firstly, I've just got a little video for you guys as well. So I think this one is just some like study tips from our other tutors. So we've got from Chelsea, Susan, and Ethan, who tutor some of our other subjects. All right, so I'll just check the audio and everything's sharing. All right.
Okay guys, my biggest tip for the end of year exams, which is also a tip that got me through high school,
Is to write practice essays and also practice plans.
Number one, make sure you understand and you write your own summary book and you know every little nook and cranny of it, because this is what's going to save you in your exam too.
When you're preparing for exams, you want to make sure that the way you're preparing and doing practice exams is as close as possible to what the real situation is going to be like. And I don't mean just making sure that you do it under time conditions and that you also have your notes next to you. I mean setting out your table the way that you would on the actual exam day.
And tip number 2 is practice, practice, practice.
Practicing your writing is the best way to prepare for that end of year exam. And if you don't have time to write a full essay, just plan some essays and prepare for as many different scenarios as you can.
There's so many questions in the textbook, and they'll all help you in your end of year exams, because this is the only way to get that surface knowledge and bring it deeper into your brain. And it'll help you really understand the questions and recognize what the question is actually asking for.
Right. Yeah, so thanks to Chelsea, Susan, and Ethan. Hopefully you guys found that a bit helpful. Cool. Oh. All right. So now we've got area study 4. So we're looking at vectors. So we've got vector resolutions, projections, and then linear independence and dependence, and then also vector calculus. So we're going to look at area study 4. I think area study 5 is like mechanics and kinematics and stuff. And then we've got probability. Okay. So firstly, we'll look at vector projections and resolutions. So vector resolutions, we've got the vector resolute of A in direction B is used quite a lot. So this is the formula that we're going to be using basically. So there's a few variations of it. But yeah, so either one works, but this is the one that I like. So we've just got U is equal to A dot B on B dot B times B. Okay, so A dot B is going to be a scalar, so it's just the dot product, so it's going to be sort of just a number or like a scalar. B dot B is also sort of a scalar, and then B is a vector. So in like generally it's going to produce a vector, and then this first term A dot B on B dot B is just going to scale it. All right, and the vector resolute of A in the direction of B is sort of just like the part of A that contributes to the direction of B. So I'll draw it out when we do the example. But yeah, it's a really common thing that they ask for. And yeah, in general, you use it a lot. Yeah, it's very like useful in sort of getting forces, like resolving forces in a certain direction and stuff. So yeah, I don't know if you do engineering or something, you use it a bunch as well. Okay. So this first question, we've got 2016 exam question 5. So it just says, consider these like vectors here where D is a real constant. We want to find the vector resolute of A in the direction of B. Okay, and then I think we've got, oh yeah, no, I'll go through that content afterwards. Okay, so I'll just share my screen and we'll go over it. Okay, so we've got consider these vectors. So we've got vector A here, vector B, and vector C. So they're all like 3D vectors. Okay, and we just want to find, yeah, the vector resolute of A in direction B. So yeah, okay, C isn't relevant for this question. It would be relevant in like sort of section B or whatever. But yeah, it's not relevant in this question. We just want to find the vector resolute of A in direction B. Okay, so firstly, I just write out the formula. We know the vector resolute is usually expressed in terms of a U, so it's U equals A dot B. So that's just the dot product divided by B dot B, another dot product, times the vector B. So U is a vector and B is also a vector, but we know that A dot B and B dot B are just scalars, so they're sort of just numbers. All right, and then if we draw out how it works, we've got sort of A just in some like arbitrary direction, and then B, and then the vector resolute of A in direction B is sort of just going to be the part of A that contributes to the direction of B. So in this case, or just U would be like this vector here. All right, so that's like geometrically what we're finding. All right, so firstly, I'll just like find A dot B and B dot B, and then put it into this formula. Okay, so firstly, A dot B. So it's just going to be, and I'll just write the coefficients. So A, we can just express as a vector. So 3, going to be 3, 5, -2. And then B is also a vector. So again, I'll just express it like in terms of its coefficient. So it's going to be 1, -2, 3. Okay, so to find the dot product, we just multiply it out. So it'll be like 3 times 1 plus 5 times -2 plus -2 times 3. So it's going to be equal to 3 minus 10 minus 6, which is -13. All right, and then we can do the same thing with B dot B. So B dot B, we've got just B sort of dot product with itself. So it's going to be 1, -2, 3 dot the same thing. So 1, -2, 3. So it's sort of just going to be all of its components like squared and added up. So in this case, it's going to be 1 times 1 plus -2 times -2. So plus 4 plus 3 times 3 plus 9. So it's going to be equal to 14. All right. So now we just need to combine them in this formula up here. So it's going to be A dot B, so 13 on B dot B, so 13 on 14. So we've got U is -13 on 14 times B. And B is just I minus 2J plus 3K. So that's going to be the answer. And we can just leave it like that because that's like sort of the most simplified version. Like you can expand it out and make it equal to like -13 on 14I plus 26 on 14J, etc. But this is like a perfectly fine way to leave it. So yeah, don't do too much work if it's not required. So I would just leave it as it is. All right. So that's the end of that question. So we've answered it by giving the vector resolute. So we'll go back to the slides. Okay. So now that we've done that question, we'll do the next sort of vector one. So now we're looking at linear dependence. Okay, so we can say a set of vectors are linearly dependent if you can express one vector using sort of like a combination of the other two with different sort of scalars. All right, so for example, we've got this set here. We've got one vector is I plus j, one is 2i, and one is -j. So because we can write I plus j like one of the vectors, and it could be any one, like, but in this case, we've just done this one because it's the easiest. So because we can write like I plus j equals some scalar, so in this case, it's a half, times the first vector plus another scalar, which in this case is -1, times the second vector, we can therefore say they're linearly dependent. So basically, if we can express one vector as the sum of the other two with two different scalars, then they're linearly dependent. Okay, and at the same time, like we can say they're linearly independent if this is impossible. All right, so now we'll just do this example to sort of go through it. Okay. So got it here, linear dependence. All right, so basically we can say, yeah, so it's saying these vectors, so A, B, and C are linearly dependent. And then it just wants us to find the value of D for which they are linearly dependent. Okay, so basically we can say that they're like linearly dependent if we can express one vector, and we can say like any sort of any order, but I'm just choosing A because it's like the first one. So if we can express one vector as the sum of the other two with some like coefficients. So we're going to say B is like the big B is the coefficient times B plus big C times C. All right, so if A is equal to B times B plus C times C, and there are like actual values for B and C, then they're going to be linearly dependent. So basically we're going to be solving for like B and C, and therefore we're going to sort of find D on the way. All right, so now I'll like rewrite this. So we can say A is 2i minus 3j plus 4k. And then that's going to be equal to, so B times B. So -2i plus 4j minus 8k plus C times C. So plus C times this one here. So -6i plus 2j plus dk. Okay, So now we'll expand it out and collect like terms, like as usual. So that there, so we've still got the same left-hand side. Is equal to, so we've got negative 2bi plus 4bj minus 8bk plus negative 6ci plus 2cj plus dck. Okay, cool. So yeah, we could skip that line, but I'll just write out sort of all the steps. So now we can collect like terms. So we'll collect like the I terms, the j terms, and the k terms. So now we can say negative 2b minus 6ci plus 4b plus 2cj plus negative 8b plus cd, so plus negative 8b plus cd times k is equal to like 2i minus 3j plus 4k. Okay, so you have to equate like terms like all the time and such, so we're going to do that again. So we can equate the I terms, so then we get 2 equals negative 2b minus 6c. So dividing that all by 2, we get negative b minus 3c is equal to 1. So that's sort of our first equation. And then now we can equate the j terms, so then we get 4b plus 2c is equal to negative 3. So this is sort of our second simultaneous equation. So now, because both of those equations are in terms of b and c, we can just solve them. So we'll just do equation 1 times 4, so we can work it out. So that's going to be negative 4b minus 12c is equal to 4. All right, so we can write that as sort of as equation 3. So I like to do it, and then we can just add those ones up. So we're not equation 1, we'll do equation 2 plus equation 3. So that's going to be, the b is going to cancel out, and then we're going to get negative 10c is equal to 1. Therefore, c equals negative 1/10. Cool. Okay, so we've got a c value, and now we can sub this back into one of those equations and get our b value. So I'll just sub that back into like equation 1. So then we get negative b minus 3 times c, so sort of plus 3 on 10 is equal to 1. So then therefore we get b is equal to negative 7 on 10. Okay, so we've got our c and b values. All right. So now we'll look at the k components. So we get 4 is equal to negative 8b plus c times d. So we can sub in our c and b values in here. So 4 negative 8 times negative 7 on 10 plus c, which is negative 1/10 times d. So now we're just solving this equation. So multiplying everything by sort of 10 and simplifying it out, we get 40 is equal to 56 minus d. Therefore, d is equal to 16 is our solution. Okay. So you can see we've just like applied the linear dependence formula here, and then equated like terms, and then from that we can solve for our 3 unknowns. So our 3 unknowns b, c, and d. So firstly we've got b and c, and then therefore we can find d. So basically this is saying this is like the only value of d for which all of those vectors will be linearly dependent. All right. So now that we've done that, we'll get on to the next thing. So now we'll be looking at vector calculus. So it's quite similar to just normal calculus, but it's just like stuff expressed in vectors. And we can see it's kind of just like parametric equations, sort of. So we've got one vector equals 2 plus t in this case, times I, which is just sort of the I component, like in the x direction, plus another equation, so 4t squared minus 1 times j. So that one's just in like sort of the y direction or the j component. All right. So this is an example of vector functions, and sort of vector calculus is like the study of vector functions. Okay. So as it says, like the beauty of this, or like the why it's helpful is that we can just like restrict the scope of what we're looking at to individual components. So this happens quite a lot in like kinematics. So we might only be considering like the J component. So like, I don't know, a ball might have been thrown and we only care about when it hits the ground or something. So yeah, we can restrict it like this, but we'll get into a little bit more of like kinematic stuff in the next area study. But anyway, now we've got just another question. So this is another sort of hard one, and it's like the last hard one, in my opinion, or the last difficult one for at least my section. So again, it's question 10. So it's like one of the last ones, and it's 5 marks. So it's like another big question, but it's at least the last big question for my part. So yeah, so we've got the position vector of a particle moving along a curve at t seconds is given by this sort of vector equation here. And it says t is between 0 and 1, and then the distances are measured in meters. Yeah, so this is sort of just giving the position at a certain time, and it's measured in meters. All right, so, and then it says d, the distance d meters that the particle travels along the curve in 3/4 of a second is given by this equation here. So it's just an integral, and then it wants us to find a, b, and c. Okay, so let's get into it. Okay, yeah, so I included the again, the marking sort of spectrum again. So this one seems to be sort of even harder than the other ones, just because like barely anyone got the higher marks. So we can see only like 2% of people, and this is 2% of people in Spec got 5 marks. So it's pretty hard. For some reason, 0% got 4. And then most people didn't do that well. So most people got like 0 or 1, and then a few people got 2 or 3. All right, so it is just quite a hard question in general. So there's like a bit of a tricky bit that's like relying on our understanding. But again, it is also just question 10. So people, like a lot of people might just not have had time to get up to this. So there's sort of 2 reasons for the marking spectrum. Okay, so for this one, we've got, yeah, so a position vector defined by this. So this is sort of like our x component, and this is like our y component, or like our I and j components. And we've got components. So, and then we've also got a domain, t is between 0 and 1. So it's between 0 and 1 seconds. So the distances are measured in meters. All right, so that's going to be our unit. And then finally it says the distance, d meters, that it travels along the curve in 3/4 of a second is given by this. All right, so basically we're going to use the distance formula. And we're going to use sort of the parametric version of it as well. So it's actually basically the arc length formula. So you can say like the distance, or essentially the arc length of this curve defined by that vector equation is going to be from like t1 to t2, t1 to t2 of the square root of dx dt squared plus dy dt squared. dt. All right, cool. So we can say the x component is sort of like equal to x. So we can split this up and say x of t is equal to this like x component, so t cubed on 3. And then we can also say y of t is equal to the other side. So y of t is arc sine or inverse sine of t plus t times all of that, so 1 minus t squared. All right, so now I'm going to sort of bring them down and just work out their derivatives. So the x squared one's not too bad. We've just got x of t is t cubed on 3. Therefore, x dash t, the derivative, is equal to t squared. Easy, okay. And then y of t is a bit harder to work out. So we've got y of t is, as I said, inverse sine of t plus t times root 1 minus t squared to the power of a half. Okay, so we just need to work out the derivative of these ones. All right, so we're just sort of using the product rule for this one here. And then on this side, we're using the derivative of like inverse sine. So that one's just on your formula sheet. If you guys haven't memorized that, that's fine. but we get the derivative for the first one. So this inverse sine t one is 1 on root 1 minus t squared. And then using the product rule, we sort of go like u equals t, u dash equals 1, b equals 1 minus t squared to the power of a half. And then v dash is the derivative of that. So the derivative of that is going to be like a half times -2 times 1 minus t squared to the power of negative a half. So it's actually going to be equal to, negative t on root 1 minus t squared. Basically, that sort of boils down to. All right, so then the derivatives of these ones are going to be, so d on dx of just that term there is going to be negative t squared on root 1 minus t squared, plus root 1 plus t squared. All right, so we can simplify this by putting the second term, so this one here, on root 1 minus t squared as a denominator. So we can sort of times that by 1 plus t squared on root 1 plus t squared. All right, so then when we separate this out, when we simplify this down, it's going to be equal to 1 minus 2t squared on root 1 minus t squared. Okay, and that's like literally just the derivative of that term there. So that was like a little bit of work to work that one out, but we're done. All right, so now we can put this all together and we can say that the derivative of y, so y dash t, is equal to the derivative of inverse sine, so 1 on root 1 minus t squared, get 1 on root 1 minus t squared, plus my 1 minus 2t squared over root 1 minus t squared. All right, so that's the derivative of inverse sine plus the derivative of the other term. So we finally combine them. All right, so now combining them, they're already on the same fraction, so that's easy. So then it's going to be equal to, equal to 2 minus 2t squared on root 1 minus t squared. So that's going to be like 2 times 1 minus t squared on that. So therefore, we can simplify this down to 2 1 minus t squared on root 1 minus t squared, which is just 2 times root 1 minus t squared. Okay, so finally we found the derivative of y with respect to t, and we've also got the derivative of x with respect to t. So we can put them in the distance sort of formula that we wrote out before. So we've got distance is from t1 to t2, so from 0 to 3/4 of the square root of x dash t, which is just t squared plus y dash t squared dt. All right, so we'll keep going with this one. So 0 3/4, that's going to be the square root of, and all of like the inside of that is going to separate out into t to the power of 4 plus like 4 times 1 minus t squared. So it's going to be t to the power of 4 minus 4t squared plus 4. Yeah, so just skip one little line just so we sort of keep to the time. Okay, and then that's going to be equal to 0 to 3/4 of the square root of t squared minus 2 squared dt. So we just need to recognize from sort of the coefficients and stuff that 0, -4, 4, that's going to be a perfect squared, and it's going to be t squared minus 2 squared. Cool, okay. So this here is actually going to be equal to 0 to 3/4, and it's going to be plus or minus t squared minus 2 dt. All right, so it's going to be plus or minus that, and now we just have to pick which one. All right, so this is sort of the most difficult little section of this question, in my opinion. So now we just need to pick if it's plus or minus, basically. So from above, we know that the domain is equal to, so from 0 to 1. And we know that because this is a practical question, because it's asking us for the distance, we know that the distance d must be positive. And because of those two things, so because the domain is between 0 and 1, and because d must be positive, we therefore know, sort of if we graphed out t squared minus 2, we're looking at, that was bad. If we graphed out t squared minus 2, we're looking at this function here. And basically the domain we're looking at is down here. So t squared minus 2 is positive, but if we take the if we take the negative of that, it's going to be positive. If we take the negative version of this, it's going to be positive, which is what we wanted. So basically we have to take the negative version. It's going to be equal to 0 to 3/4 of negative t squared minus 2. So of t minus 2 squared dt. And that's going to be the equation. So they didn't want us to work it out. They just wanted us to get it in this form here. So sort of like a quadratic form. So that's going to be the answer for this one. All right. But yeah, as I said, I think the hardest part of this one is working out whether we take like the positive or the negative version of it, basically. All right. So I'll go back to the screen. But yeah, we are like running a little bit low on time, so we might have to sort of move on to probability. But I will explain the next question. Okay, so my last area study that I'm going over is area study 5, which is mechanics. So basically we're looking at resolution of forces for this one. All right, so the question we've got, this is just a little bit more content. So basically these are sort of the main formulas that we're looking at. So the main formula that always comes up is like net forces will be 0 in equilibrium. And also the weight force is equal to mass times gravity. So those come up all the time. I would suggest like memorizing those. I'm sure you will have by the time you've done some exam questions and stuff. And then these are some like other useful formulas. So F equals ma, that one always comes up. So that's net force is equal to mass times acceleration. And then also we've got this sign rule here. All right. Sorry, the slides are not visible. All right, hopefully that is better. All right, and then we've just got this last sample exam question. So I might just show you the version that I've already sort of worked out. Hopefully it's like readable, but I'll show you that version just because I don't think we have time to do the whole thing. But it's not too bad of a question. It's basically just asking us to resolve some forces. All right, so I'll share my OneNote, but I'll share my like working one. Okay, this is going to be a bit messy, but it does like cover the solution. All right, so basically we've got a flower pot of mass n kilograms and it's held in equilibrium by 2 tight ropes. So this rope like T1 and T2. So those are the tension forces. Okay, and then it tells us that one rope makes an angle of 30 degrees, has a tension of T1, so that's that one, and then the other is T2, has a angle of 60 degrees. And then we've got the box is m kilograms, so therefore we can infer that has a force of like mg down, so that's the weight force. So the first question is show that show that T2 is equal to T1 on root 3. So this just requires us to resolve the forces. So firstly, we have to just show like what we're using. So we show that J is in that direction, I is in this direction. And we're just gonna, for the first question, we're just gonna resolve them in the I component. So we know that in the I component, it's gonna be T2 times sine 60, just using like trig, minus T1 times sine 30 are gonna be equal to 0 because it's in equilibrium. We can continue to solve that. Then we'll get T2 is equal to T1 times root 3. So we're just using our exact values and resolving in the I component. All right, and then the next question is like just a little bit harder. So it's just saying that like the first rope is strong, the second rope will break if the tension exceeds 98 newtons. And then it just wants us to find the maximum value of M for which it'll remain in the equilibrium. So basically we're just going to make T2 equal to 98 newtons because we know that's the maximum that it can be. And then we're going to go along and solve for M. All right, so if we make T2 equal to 98 newtons, we can find T1 based on the equation before. And then we want to find the resolution of forces in the J direction. So that will be T1 times cos 30, T2 times cos 60 minus mg equals 0 because we know it has to be in equilibrium. We'll sub in all of our values, solve for this, and therefore we get M is equal to 196 on G, and we know G, like the sort of force of gravity, is equal to 9.8. So that's going to be 196 on 9.8, which is equal to 20 and you need to include a unit as well. So it's going to be 20 kilograms is going to be the mass. All right, cool. So that's the solution for that one. So I might stop sharing and pass it over to Arndt, just because we need to get into the probability section.
Yep.
So yeah.
Okay. I'm gonna have to go through this quickly, but that's fine. Okay, so so for probability and statistics, so I'm just gonna go through types of variables, random variables, combinations of random variables, sampling and distribution of sample means, confidence intervals, and hypothesis testing. So the two types, you have the discrete and continuous. So discrete is just like or how many students, and then continuous is like like measuring height. So for your expectation or your mean and your variance, so pretty simple. So if you have your variable here and you have a constant attached to it, you would bring it out like this. And then if you have a constant on the inside, you just drag it out. And then if you extend it to two variables, so same thing applies, you drag out the A and then you drag out the B. So basically here, pretty simple. And then for variance, the only difference is that you square the number. So you would take it out and then you will square it. And you see here, B just kind of disappears because one thing to note is that variance is your spread. So having the B there moves the distribution, but it doesn't really change the spread. So that's why B disappears. But yeah, it's not too bad, hopefully. And then for here, it's just the same rule with two variables. So you would square the number here, and then you would square B here. Hopefully, it all makes sense. All right. So the only tricky bit is that when you add them up and you split the two variables, it works fine. It looks normal, but when you subtract it, so it's EX minus EY here, but for some reason, it's VX plus VY. So you can think of it as this. So technically, there's a 1 here and there's a 1 here. So here, you're doing 1 squared, and then here, you're basically doing, so that's technically -1. So you would be doing -1 squared. So that's it. Pretty simple. It's not too complex. So let me have a look. Okay, so for this question, so basically, your X and Y both have a mean of 4 and a variance of 9. So all it's asking for is for this variable Z, which we define it as AX plus BY, what is the possible values of A and B? So pretty simple. All we have to do is say that the mean of Z is just equal to mean of AX plus BY. So they've basically told us that the mean of Z is 8. So 8 goes here, and applying what we learnt before, it's basically just A of EX plus B of EY. Okay, so if you remember, X and Y have the same mean. So all we have to do is just substitute it in. So 8 is equal to 4A plus 4B. So that's basically our first equation. Now, to find the second equation, do the same thing basically. So we know that the variance of z is equal to okay, so they've told us variance 90. And if we expand this, we would get a squared VRX plus b squared y. Okay, and then 90 is equal to, what's the variance for each of them? So it's 9. So it's 9a squared, 9a squared plus 9b squared. There's your second equation. Now all you have to do is just simultaneous equation, and then you'll get, see, not too complex. Now for sampling, pretty simple. If you have a population and you grab the sample, yeah, it's not too complex. And so when you grab the sample, your goal is to try to infer information that can be translated to your population. Okay, so, all right, so for sampling distribution of sample means, basically, if your original had mean of mu and variance of sigma squared, then for your sample means has this. So the mean, oh wait, no, the mean is kept, but your variance, so your variance is just equal to your original standard deviation squared divided by n. And that's about it. Oh, n is your sample size. Okay, basically to sum up your confidence interval, so if you think of it as a bell curve, so so using this as an example, what this is saying is that from the middle, which is your sample mean, or your population mean. So if this is your population mean, you're going 1.96 standard deviation to the left, which is this part, and then you're going 1.6 standard deviation to the right, which is this part. And that covers 95%. So if you visualize it as a bell curve, so if you're going this way by 1.96, I'll just say SD, standard deviation, and then you're going this way by 1.96 standard deviation. Basically, you're saying this whole area here is 95%, which is what this is saying. Yeah. Hopefully that wasn't too complex, but yeah. Okay, what's next? Okay, so as a example, let's see. Okay, so it is known that from past experience. Okay, so our population mean is 275, and our population standard deviation is 15. So let's see. Okay, so the goal is to select 2 independent variable samples with sample sizes of 50. Okay, and then for A, assume that the machine is working properly. Find a probability that at least one random sample. Okay, so basically there's 2 parts. So first of all, we need to find what is the probability that the mean mass would be in this range. So to do that, first we need, we need the mean of the sample mean. So that would equal to the original population mean, which is equal to 375. And then for the standard deviation, is basically the original standard deviation, so 15, divide by, okay, so we know that the sample size is 50. So we have 50 here, and we square it. So if we simplify this, so 50, so root 50 is basically just, what is it, 5 root 2. So if we simplify that, is 3 over root 2. You don't have to simplify it, but I'm just writing it. So it's much more simpler after. But, so knowing this, now if you find the probability that your sample mean lies in this range, 375. Okay, so now if you do on your calculator, so norm CDF, yeah. So your lower, your upper, your mean, and your standard deviation, which we said was 3 over root 2. So once you do this in your calculator, and it should be approximately, what is it, 0.4908. So that's one part done. So we basically found the probability of the mean mass being in that range. Now, it's asking for what is the probability that I pick up 2 samples, so 2 independent samples with what is it, sample size of 50. What is the probability of those 2 being in this range? So all we have to do is make a new variable. So we'll say y. In this case, if you haven't realized, it's just a binomial. So binomial, and then we have, so our n would be 2 because it's 2 samples, 2 sets. So it'll be 2, and then the probability of it being in this range is this number here, 0.4908. So basically, to find the answer, you would do binom CDF. So sample, your n is 2, your probability of success is 0.4908. Your lower bound is 1, and your upper bound is 2, because it's asking for at least 1. At least 1 will have the mean mass in this range, and your max would be 2, since you have two sets of samples. And if you do that, it should give you 0.741. 3 decimal places, because that's what they're asking for. Yeah, hopefully that wasn't too hard. Okay. Okay, we are almost done. Okay, hypothesis testing. So H1 and H0, H1 is just saying, so when you grab the sample and you get a sample mean, H1, H0 and H1 is basically saying, is it possible that that sample came from the original population? So let's say if the original hypothesis was 100, so the mean from the population is 100. But let's say if we grab the sample and we get, let's say, 150, we're basically checking for the likelihood of that happening. So H1 would be the alternative hypothesis. So it would be like, let's say, okay, so we'll use this example. So we'll say, maybe it came from a population with a much higher mean. Yeah, that's basically it. Not too complex. Also, for your alternative hypothesis, you can have less than, or you can have not equal to. So not equal to is when you would do two-tail. I'll try to explain it afterwards, but yeah. Okay, and then for your p-value, it's basically, okay, so p-value is basically this. This is all you need. So the p-value is the probability of an observed or more extreme result arising by chance. So as I was saying before, if, let's say the original mean was 100, and this was 150, let's say, is equal to 150. This is basically the likelihood of getting 150 or beyond that, which is the probability of observed or more extreme. And it should be expressed as a percentage. But yeah, I think we're almost out of time. Yeah, okay. We'll have to skip this question. But one last thing to note is that there are two types of errors. So you have type 1 and type 2. So type 1 is basically saying if your null hypothesis is true, but you reject it, but you reject the hypothesis, you're wrong. So that would be type 1 error. So it would be a false positive. And then let's say if your null hypothesis is actually false, but you don't reject it, then it would be type 2 error. So it'll be false negative. Okay, I think that wraps up everything. All right, back to you, Saskia.
All right, perfect. Thanks, Nat. Thanks, sorry, for going over the probability section. That was great. Yeah, so I think Yang sent a little link in there, just asking you guys to do the survey just about this session for your chance to win a $50 voucher. And of course, it's also just really helpful for us if you guys give us some feedback. So hopefully you can see the slides. I'll just go through them. But I think we should have, yeah, so we've got the QR code here that you can access the survey. So if you could do that, that would be great. But yeah, otherwise, yeah, while you're doing that, I don't think we have any other Menti questions at the moment. I'll just check for a sec. Yeah, did we already ask them? Yeah, no, I believe we answered all of the survey questions. So if you guys have any more, feel free to ask us. But just while you're doing the survey, maybe if everyone like on the panel could just share like a little exam tip or like something that they want to leave the students with. So yeah, maybe Yang, do you want to go if you're there?
Hi, sorry, your voice is cracked up a little bit.
On the side. Can you hear now?
Oh yeah.
Yeah. There's a couple of questions in the Menti. So we'll just go over those. But yeah, if you guys could just do the quiz now, that would be great. But yeah, okay. So the questions on the Menti. I think that one's answered. But yeah, of course, it'll be possible to get the slides. We'll give you guys all the questions that we went through, like from the OneNote and everything. See if there's any others that we didn't answer. Also, if you guys have any questions now, feel free to put them in the Menti. Like, yeah, I don't think there's any others that we haven't answered yet. Okay. Actually, this one looks like a new one. Okay, so in two-tailed test, why do we need to double the p-value? Okay,
I shall explain this. Okay, so basically, yeah, when you do one tail, so let's say when you do less than, you get because like if you think about it, doing less than or equal or greater than gives you the same p-values. So one tail will give you half, and then doing two tails will give you 2 of the p-values, if that makes any sense. Because when you do two tail, you're not saying less than or greater than, you're saying it's both of them. So I hope that makes some sense.
Yeah, no, I think that makes sense to me at least. But yeah, it's sort of like a combination of both the tests. So that's sort of why you need to double it, if that makes sense. All right, and then there's another one. Is collinearity necessary to know? Yang, do you want to answer this one? Or on?
Wait, what was the
Okay.
question, sorry?
Can you see my screen, by the way?
Oh, yeah.
Yeah, so it's just, is collinearity necessary to know?
I'm pretty sure. It's just good to know what it is. Even I don't remember. What was it again? It's like when
I don't remember what it is either. That's why I was wondering if it was there.
Let me check
but
my
yeah. I feel like, I mean, anything on the study design is necessary to know. Can't exactly remember what collinearity linearity is.
Is it vector?
Yeah, Nyang, do you just want to answer the question?
I don't think it's gonna be in the exam, but
yeah, so I'd say it's maybe like just a sort of random point in the study design, like stuff like that. I feel like it's very unlikely to be on the exam, so it's probably not that necessary to know it. But if you just want to have, like, if you're aiming for like a 50 or like a 48 or whatever, I reckon try and revise everything, like if you're aiming for the high marks, but otherwise probably not that necessary, just like the main sort of content that you can do. But if you do like a lot of exams and stuff, you'll encounter basically all the questions that they'll ask you anyway, so you'll sort of figure out like whether it's likely that it's on the exam. But yeah, so if you're aiming for the high marks, I reckon I would go over random stuff like this, but otherwise don't worry too much. Okay, so another one. I find graphing such working with complicated functions that aren't exactly studied difficult to handle, such as that one. How would I strengthen myself in these areas? Yeah, I feel like a lot of people struggle with this because they can ask you questions about a lot of like really random looking functions in Spec. So generally like rational functions and stuff, you'll be expected to be able to graph. I would say follow the steps that we did at the very start. So start by trying to factorize the denominator, and you can try and like expand it by putting it in partial fractions. That might make it a bit easier. But other functions that are really hard, like e to the power of f of x, if you need to visualize them somehow, like to graph it or something, like they won't ask them if they're too hard, but if you do need to do them, I would say graph sort of each individual function. So I'd say graph f of x, and then maybe graph just e to the power of x or something as well. And then basically you're putting one function into the other. So you're putting f of x, you're replacing x with f of x. So you can try and sort of look at how it would work. It's quite a difficult sort of technique. But yeah, I would say that's the easiest way to do it. So graph sort of both of the functions and then try and in your brain sort of put one into the other. But yeah, this is like quite a difficult part of the study design and stuff. But do you guys, Nang or Angie, have any advice for this one?
Oh yeah, for this one, I recommend just not for every graph, I recommend you guys to find the asymptote. Always trying to find these 4 points first. So that would be asymptote, x and y intercepts, turning point, and limits. Sorry, like as x approaches to infinity, what your graph gonna look like. After you find those, you pretty much can graph any graph.
No, that's really good advice. Cool. All right. And then we've got a few more. Do we need to know about sequences and series for the exam? I feel like because it was only covered at the start of the year, it wasn't seen as too necessary. Nang, what do you think about this one?
I think it's only in Unit 1 and 2 for this. So it's
Yeah.
not in your Year 12 exams.
Yeah, no, I think I agree. I don't remember it being like at all on my Year 12 exam. So I think, yeah, probably no for that one. All right. Oh, why is this highlighted? A couple more. Okay, so when we integrate something over like 1 over x, do we need to mod the log? Yeah, okay, so technically you do. Yeah, I think I did a question on this where it's like log EV or something. Like technically you do need to modulus the log. Like if your solution's only in the positive range, it's not that necessary, but yeah, technically you do. Okay, next. How would I skip some points? I feel like if I skip, I'm much likely to forget where I'm at. I'm much more likely to forget where I'm at. Oh, yeah. So in the exam, if you're actually skipping them, I would say, like in reading time, you can't mark the pages or anything. But once you're in the exam, I would like actually just fold down the pages or like highlight some sections. Like if you skip the question, I always draw like a little asterisk so I can come back to it. So I would do that. So just make some markings. So it's really obvious like which questions you skipped and which ones you want to come back to. Yeah, anyone else have any advice for that one? Cool. All right, last one. So any tips for integrating unfamiliar functions / figuring out how to integrate it? Well, I'll go quickly and then I think I'll pass on to Nyang. But for this one, I would say, yeah, like in special, you can be given some really random stuff. Like some of the ways to integrate that, like you can't or otherwise do it would be like the U substitution is a common one. Otherwise, if like you're really struggling, stuff like separating it out into like partial fractions or separating fractions out often helps. Yeah, Nyango, and do you have any advice for this one?
So for these kind of questions, I feel like the more you do, like you are going to get really like familiar with like the forms. So when you look at it, you should know what to do, even though it's different like numbers, but it's pretty much Year 12. Spec is very repetitive in terms of like integration. So as long as you do enough, you can, I'm pretty sure you can like recognize what to do.
Yeah, no, that's definitely true. And Justine, sorry, did you have any advice for like any of these questions since this is the last one? Or any advice for the students?
For integrating, I'd say always check for like trig identities and other things. If it's more complicated, it's probably gonna be something trig. In general, like it's really like try it, but sleep is important.
Yeah, no, exactly. All right, I think we're at the end now. So thanks everyone so much for coming. And thank you for like filling out the survey if you guys had a chance to do that. But yeah, just on the behalf of all the panel, thanks guys and good luck for all of your exams and everything. So yeah.
All right, thanks guys.
Thanks.
Thank
Yeah, I might
you,
just share the pardon. Yeah, I'll just share the last screen just for everyone exits. Ooh, okay, that doesn't work, but thanks guys.